This video will give you the steps for drawing Lewis structures. Please follow these steps very carefully, including the conventions, such as not using brackets when you draw Lewis structures for this course. So the first step when you're drawing a Lewis structure is you need to count the number of valence electrons for the whole molecule. The second step, we say establish connectivity. For the most part, we will have a central atom with multiple things attached to it. And so establish connectivity here. The first atom listed is the central atom. Unless it's hydrogen, right? Hydrogen can't be a central atom. And the reason that hydrogen is listed first, even when it's not the central atom, is because we tend to list the elements in order from least electronegative to most electronegative. So you'll see hydrogen listed first for that reason. If it's not clear which atom is the central atom, or if it's not the first atom, I will sometimes underline it for you. And if you're not sure, you should start by using the least electronegative atom in the center. The next step is to connect adjacent atoms with bonding pairs. Then add lone pairs to complete the octet on the outer atoms. So don't do the central atom when you're doing this initial add lone pair step. Then push electrons to create multiple bonds. And we will go through an example. So if you don't quite know what that means, don't worry. This will be part of how we get octets around the central atom in case we ran out of electrons when we were doing lone pairs. Step 6, you will need to calculate the formal charge on every atom and write in any non-zero formal charges, which I'm going to start to abbreviate FC, next to that atom. So no brackets. I know you will see brackets in the keys for the textbooks. You will not be allowed to use brackets around the molecules that you turn in, and you won't see them around the answer keys that I write for the problem set. So we have seen with hydrogen that it is an exception to the octet rule. There is one general other case, but I want to make sure that you have both of those listed here. So exceptions to the octet rule: hydrogen and helium only need 2 electrons. The second, we'll call this set of exceptions, are for some electron deficient atoms. So you will find that some atoms, including things like boron and aluminum and others, are happy with fewer than 8 electrons. So specifically, these two are happy with only 6 electrons. And the way that you will be able to tell that they are happy with only 6 electrons is when you calculate the formal charge will be 0. So this formal charge step will be really important. All right, so I guess I should give you an equation for calculating formal charge before we get into these examples. So this will be for each atom. So you'll do this if you have 5 atoms in your molecule, you'll calculate the formal charge 5 times. Now, you won't actually have to do it 5 times, as you'll see in the examples, depending on what's in there. But you will need this equation. So the formal charge is the number of valence electrons minus the number of lone electrons. Notice this says lone electrons, not lone pairs. We're going to count those electrons individually, and then minus 1/2 of the bonding electrons, again counted individually and not as a pair. Okay, those are all my steps. Let's do an example. So a great example to look at is NH3. So if I do my steps in order, the number of valence electrons, nitrogen has 5. Then there are 3 hydrogens with each having 1. So my total valence electrons for this molecule is 8. Nitrogen is listed first. So this is my central atom. So establishing connectivity, it's nitrogen in the middle and then 3 hydrogens attached to it. So we'll usually just kind of write nitrogen and then write the hydrogens around it. My third step is to connect adjacent atoms with bonding pairs. So connect the hydrogens to the nitrogen with single lines that represent an electron pair, right? Those are bonding pairs. Add lone pairs to complete the octet on the outer atoms. Well, my outer atoms are hydrogen, so they don't need any extra electrons. If I count how many electrons I've used up here, I've used 2 per bond in 3 bonds. I've used 6. I've got 2 more that are available based on my count of 8 valence electrons. I'm going to put those as a lone pair on the nitrogen. So my nitrogen feels like it has an octet. I've used up 8 electrons. My hydrogens feel like they have a noble gas configuration. So this is looking pretty good. I don't need to push any electrons, and I can check this by counting how many electrons I've used and whether or not everyone has what they feel like is a full set. We'll see some examples where we have to push them, so don't worry about that yet. And now I just need to calculate my formal charge. So formal charge for nitrogen, it has 5 valence electrons minus, it has 1 lone pair, so it has 2 lone electrons, and it has 3 bonds, which is a total of 6 bonding electrons. 5 minus 2 minus 3 is 0. Well, that's great. And then hydrogen, we'll label these A, B, and C. So hydrogen A, hydrogen has 1 valence, 0 lone, and 1 bond, so 1/2 of 2. 1 minus 1 is 0. Now, if you take a look at hydrogen B and hydrogen C, they're in the exact same situation, right? Hydrogen B, 1 minus 0 minus 1/2 of 2. Hydrogen C is exactly the same. We'll go ahead and write it out for this one time. If they look exactly the same, right? They have the exact same number of lone electrons, the same number of bonding pairs that they're connected to. You only have to do this calculation once. You don't have to do it 3 times. If you've done it 1 time and another identical atom has an identical bonding situation, just use that one calculation. So these are all 0, so I don't need to write them on here. So this is my final structure. Now this does not show geometry or indicate shape in any way. It's just how are these atoms connected with electrons in this molecule. One more example in this video. I want to look at H3O plus, or hydronium. So hydrogen's listed first, but remember it can't be the central atom. So oxygen is my central atom. I need a count of valence electrons. So oxygen has 6. Each hydrogen has 1, but my molecule overall has a positive charge. So I have to account for that when I am counting up my valence electrons. So this -1 is to account for the fact that cations have fewer electrons. So when I add all of these up, 6 plus 3 minus 1 is 8. So I've got my valence electron count. The connectivity, we figured out oxygen is in the middle. So we'll put oxygen in the middle here and the hydrogens around it. It's kind of starting to look like the nitrogen example. Connect them with bonding pairs. Put lone pairs around the outer atoms first. Hydrogen doesn't need any. I've, again, just like with the NH3 example, used up 6. So I have 2 more electrons. I'm going to put those on oxygen. Everybody looks like they have either an octet or the 2 electrons for the noble gas configuration. I don't need to push any electrons, and I do need to calculate formal charges. So hydrogen, you won't be surprised at what this looks like. All of the hydrogens look the same, so we'll calculate it once, and they look exactly the same as they did in NH3. So 1 minus 0 minus 1/2 of 2 is 1. No, that's not 1. 1 minus 1 is 0. Oh my goodness. All right, so 0 formal charge. Hopefully, if you're falling asleep listening to this, that helped you pay attention. Oxygen, 6 valence electrons. It has 2 lone electrons and 1/2 of 3 bonds connected to it, which is 6 electrons. 6 minus 2 minus 3. 6 minus 2 minus 3 is plus 1. Yep, okay, definitely did that right. So I finally have a non-zero formal charge. I need to put it next to that atom on my structure. So this plus charge is going to go next to the oxygen, and we're going to put it in a circle. So it's really clear that this is a formal charge, and it's not like a stray mark on the paper or anything weird like that. So this is my final structure now. Oxygen, 3 hydrogens attached to it, a lone pair, and a formal positive charge on the oxygen. And then one note that I want to leave you with at the end of this video is just a note about formal charge that will help you in cases where you have multiple atoms with formal charges in a molecule. This is that the sum of all formal charges in a molecule equals the overall charge on the molecule. So if you are unsure if your formal charges are correct, this is one of the ways that you can check them.